Natural and synthetic graphite are used to construct electrodes in major battery technologies. Laptops, mobile phones, smartphones, tablets, and electric vehicles have increased the demand for graphite. As an example, a lithium ion battery in a fully electric Nissan Leaf contains nearly 40 kg of graphite.
Today, we are going to discuss close packing. The constituent particles in a solid are closely packed, leaving minimum vacant space. We are going to consider the constituent particles as hard spheres and are going to generate the three-dimensional close packing. The first step is the close packing in one dimension. Look at this figure. You can see the constituent particles arranged in a line, that is in a single dimension. This is the only possible arrangement of constituent particles in one dimension. If you take any particle, you can see that it is in immediate contact with two others. So the immediate number of neighbors for any particle in a close packing is defined as the coordination number of a close packing. So here in one dimensional close packing, the coordination number is 2. See, the definition for coordination number is number of immediate neighbors for any particle in the close packing. Next we can see the close packing in two dimension. Close packing in two dimension are of two types, the square close packing and the hexagonal close packing. We have the one-dimensional row in this direction, and if you place spheres immediately below the spheres of the first layer, you get the second dimension in this manner, and the second row is similar to the first row. Hence, they can be marked as AA type. Now here, in the second case, it's known as hexagonal close packing. The spheres of the second layer are placed in the depressions of the first one. So you have a different layer known as B, and the first one can be marked as A. So the arrangement in hexagonal close packing is AB type, and in square close packing is the AA type. Now we'll have a better view of the close packing. In the square close packing, you can see it very clearly. The spheres are placed immediately below the spheres of the first layer, and in the second case, this is the HCP or the hexagonal close packing. In that, the second layer spheres are placed in the depressions of the first one. Now what about the coordination number? You take this particle. It is in contact with this sphere, this sphere, this sphere, and this one. So it has coordination number equal to 4. Now if you join the centers of the spheres in which the particle is in contact, you get a square. That is why it is known as a square close packing. Now look at this case. If you take this particular particle, we can take a different color. Okay. So this is the particle we are considering. This particle is in contact with this one, this one, this one, this one, this one, and this one. And if you join the centers of the immediate neighbors, you get a hexagon. Hence it is known as a hexagonal close packing, and the immediate neighbors are 6 in number. So the HCP has coordination number 6 and the square close packing has coordination number equal to 4. Now look at the empty spaces in between the particles. So you can see the empty spaces in the square close packing as well as the hexagonal close packing. These empty spaces in between the close packing is referred to as void. If it's not clear, we'll take the red color. It's called void. So voids are the empty spaces in between close packing. So that is about the two-dimensional close packing. Now we'll move to the three-dimensional close packing. Okay. So in the three-dimensional close packing, you can have again two different types that is arising from the square close packing. So there were two types of two-dimensional close packing, that is the square close packing and the hexagonal close packing. Now we are going to generate the three-dimensional close packing first from the square close packing, and this is how it will look. So you have a two-dimensional layer, and if you place a similar two-dimensional layer immediately below the first one and just stack many such layers one below the other, you get this type of arrangement which is known as the simple cubic arrangement. Now what about the coordination number of this simple cubic close packing? For that, we'll take this particle at the center. The particles with which it will be in immediate contact will form the coordination number. So this particle is in close contact with this one, this one, this one. So 1, 2, 3. Then here this particle, and here this particle, and below one particle. So altogether 1, 2, 3, 4, 5, 6. So 6 is the coordination number of this simple cubic close packing. Now we'll see the three-dimensional close packing generated from the hexagonal two-dimensional close packing. The first layer is shown here by the red spheres. For better understanding, the second layer spheres are marked as black spheres. So we are going to place the second layer on the first layer. Now once the second layer is placed, you get two types of voids or empty spaces. Here the sphere, these spheres are covering the void formed by the first layer, and that void is closed because this sphere is closing the void of the first layer. And such voids, covered voids, are known as tetrahedral voids marked as T. So you can see total 5 voids here, 1, 2, 3, 4, 5. All these tetrahedral voids are closed because they are covered by the spheres on the second layer. Now there are certain other voids which are not covered. See, here also you have one void which is not covered because this void is overlapping with the void of the second layer. The void formed by the first layer is overlapped by the void of the second layer. So this void is not closed now. It can be seen through. That void is known as octahedral void and it is marked as O. So once the second layer is placed, it gives rise to two different types of voids, one known as the tetrahedral voids formed by 4 spheres, 1 on the top layer and 3 on the first layer. So inside the covered void is known as the tetrahedral void. Now the second type of void is the void which is not covered. It is formed by 6 spheres, 3 below and 3 on top. This is the void which is not covered. It is formed by 6 spheres and it is known as the octahedral void. So there are 2 types of voids, tetrahedral voids and octahedral voids. The tetrahedral void is shown here separately. The covered void and the octahedral void is shown here separately. See, this void is not covered. It is formed by the void of the first layer and the second layer overlapping. So you can see through this hole. And if you draw straight lines joining the centers of all these 6 spheres, you get a octahedron. And in the case of the tetrahedral void, if you join the centers of all the 4 spheres, you get a tetrahedron. That is why it is known as a tetrahedral void, and this one as the octahedral void. Now we'll see the differences between the tetrahedral voids and the octahedral voids. The first point, when a sphere of second layer is above the void in the first layer, a tetrahedral void is formed by 4 particles. In the case of octahedral voids, when a sphere of the second layer partially covers the void in the first layer, an octahedral void is formed by 6 spheres, 3 below and 3 above. Second point, if the number of close packed spheres be n, then the number of tetrahedral voids generated will be equal to 2n. That is, if 8 constant particles form the close packing, then the number of tetrahedral voids will be 16. That is 2 into 8, 16. And in the case of octahedral voids, if the number of close packed spheres are n, the number of octahedral voids generated will be equal to n itself. That is, if 8 close packed spheres are there, 8 octahedral voids will be generated. Then the third point constitutes 4 spheres, 3 in the lower layer and 1 in the upper layer. We have already mentioned that. And in the case of octahedral voids, constitute 6 spheres, 3 in the lower layer and 3 in the upper layer. When the centers of the 4 spheres are joined, a tetrahedron is formed in the case of tetrahedral voids. And when the centers of these 6 spheres are joined, an octahedron is formed in the case of octahedral void. So these are the differences between the tetrahedral voids and the octahedral. Now once again you may see how the octahedral void and the tetrahedral void looks inside a crystal lattice. Okay. Now we are going to place the third layer. So far we placed only the second layer in the case of hexagonal close packing. So we are going to place the third layer. For placing the third layer, we can choose 2 ways. That is, by covering the octahedral voids and by covering the tetrahedral voids. So we are going to place the third layer first by covering the tetrahedral void. So when you cover the tetrahedral void, you look at this figure, the first one here. So there is the first layer, a hexagonal close packed 2-dimensional layer. This is the second layer, B, which has got a different arrangement. Again, when you place the third layer by covering the tetrahedral void, you get a layer which is similar to the first one. So again, A type of arrangement. So this type of arrangement is known as A B type of arrangement, also known as hexagonal close packing in 3 dimension. Now the second type, by covering the octahedral void, we get a third layer C which is different from the A and B layers. So this is known as the ABC type, and this is the AB arrangement.
Example for hexagonal close packing: magnesium, zinc, etc. And examples for cubic close packing: copper, silver, etc. The coordination number for both these close packings are 12 and the packing efficiency
74%. You'll be learning about packing efficiency in the next class. Now we'll see how you got the coordination number 12 for both these types of close packing. Look at the first figure. This is for the HCP or AB type of arrangement. Take this particle, the yellow one, in the second layer, B layer, and look at the immediate neighbors or the particles with which it will be in contact. So 6 of them are surrounding it and 3 of them above it and below it. So total 3 plus 6 plus 3, 12. And in the case of C, take this particle at the center. We have 6 particles in the same layer surrounding the particle and 3 particles above it in the A layer and 3 particles below it in the C layer. So 3 plus 6 plus 3, 12. So both the close packings have coordination number equal to 12. Both the close packings have face-centered unit cells. I forgot to mention earlier that the cubic close packing is also known as FCC. I hope you understood close packing, the one-dimensional, two-dimensional, and finally the three-dimensional close packing, and how it forms the hexagonal close packing and the cubic close packing. So this is all in today's session. Have a nice day. Thank you.